This is the rank sum test. Note that the rank sum test is just a particular version of a randomization test. All we did here was a randomization test, but the test statistic we used was not the difference in means. Rather, it was the sum of the ranks. And we didn't use the original data, we first converted it into ranks. But if you give me the original data, I can convert it into ranks. The randomization test works for any test statistic, and so for this particular test statistic, I can do this. So let's talk about a couple different details here. Here's a very minor detail. Suppose that these two values had been the same, that it was 3, 3, 0, greater than 12. What I would do is I would average the ranks of these two things, and I would say 2.5 and 2.5. That's all. Depending on which software program you're using, if you don't do this by hand, which will typically be the case, these ties may be dealt with in different ways. But basically, all you're going to do is average the ranks of values that are tied. But let me change that back so that we don't get confused. Okay, so that's one detail to mention. Another thing to point out is the fact that we're taking the sum of the ranks in one group and not a difference in mean ranks. How come? How come we're not just taking the difference in mean ranks? Remember way back to high school or even middle school algebra, where one of the things that I bet you talked about was an equation for the sum of all the numbers from 1 to 10, or 1 to 20, or 1 to n, 1 to any number. It's not important for us to think too much about that arithmetic in this course, except to say that we can mathematically calculate the sum of the numbers from 1 to whatever, as long as you tell me what the highest number is. And we'll do a little arithmetic in this class. The way to think about that is just, if I'm trying to add up all the numbers from 1 to 10, I know that 1 plus 10 should be 11, and 2 plus 9 should be 11, and 3 plus 8 should be 11, etc. And I can take advantage of that counting in to figure out the sum of all the numbers from 1 to n. So I can come up with a formula if I want. Why do we care about that? Well, if I know the sum of all these numbers, just given the sample size, if you tell me there are 4 units in the data set, then I know the ranks must be 1, 2, 3, and 4 if there are no ties. That means that if you tell me the sum of the ranks in one group, I can subtract and tell you what the sum of the ranks must be in the other group. In other words, if I know, so here we can see 2 plus 3 is 5, plus 5 is 10. The sum of the numbers from 1 to 4 is 10. If I know that the sum of all these ranks must be 10, and that the sum of the ranks in group A is 5, then the sum of the ranks in group B must also be 5. And so there's no reason to compare what the ranks add up to here and what the ranks add up to here, because I know that if you give me this sum, it implies what this sum must be. There's no reason to also do something with this group. And then also note that sums and means are the same thing, right? If I can either add up a bunch of numbers, or I can add up a bunch of numbers and divide by how many there are. If I had divided each of these sums by 2 to get the mean rank in group A, it wouldn't have changed anything about what we were doing here. I just write divided by 2 under each of these numbers. It would not have changed the p-value. So why do we use the rank sum as opposed to the difference in mean ranks? First, because if you tell me the sum of the ranks in one group, I do not also need to know the sum of the ranks in the other group, because it's implied, because the total sum is fixed if you just tell me how many values there are. And we use the sum in one group as opposed to the mean of the ranks in one group, because there's no reason to divide all these numbers by 2. It doesn't help. It doesn't change anything. So the simplest solution is just to sum up the ranks in each of these.